All right, thank you. So we now have our next speaker, which is Shifan Yu from Lancaster University, who's going to talk about realized candlestick Wicks. Floor is yours.
Okay, so first of all, thank you for having me for this year's VTSS workshop. And the paper I'm going to talk about today is realized candlestick Wicks. This is a joint work with Yifan Li from University of Manchester, Ingmar Nord and Sandra Nord from Lancaster University. So let me start with what we did in this paper. So what we did in this paper, firstly, we proposed a new non-parametric estimator for the integrated volatility, for the integrated variance. So it's a new realized measure with high-frequency candlestick data. It's not only based on the returns, but based on high-frequency intraday candlesticks. So here I provide some examples here. About the high-frequency candlestick charts. And we show that this estimator is not only jump robust, but also robust to some local periods or local episodes with highly directional price movements. So in some recent literature, they call this new type of extreme events as the phenomenon of drift bursts or persistent noise. And we show that our estimator has both great asymptotic properties and good final sample performance. Now let's start with the motivation. Two questions. The first question is, why do we still need new volatility estimators with a new type of robustness, with such a drift robustness? That's the first question. The second question is, why do we like this form of high frequency data? Why do we like candlesticks? For the first question, some empirical evidence shows that now in recent years, there are more and more flash crash type events in different financial markets. So this plot on the left-hand side shows the most famous flash crash type event in the equity market, the May 2010 flash crash in the US stock market. And it shows the price pass of one of the stock indices on that day. So starting from around 2:30 p.m., the price started to drop down sharply. And then after around 20 minutes, we observe a turning point. And after the turning point, the price started to go back. So we saw a reversal. We can see a clear V shape here during this episode of flash crash. So either before or after the turning point, we see highly directional price movement. The price movements are highly directional, very sharp, but they are different from the jumps defined in the high frequency literature. It's not a discontinuous shift from one level to another level. They are more like continuous price movement, but very persistent. So this is what we call the short-lived explosive trends over this flash crash episode. And if we look at the high frequency returns before or after the turning point, like 1 minute returns or 5 minute returns, we will observe a very positive autocorrelation. So this is the flash crash event. And also in some other financial markets, we can also observe some notable episodes of flash crash, commodity markets, treasury bonds market, or in exchange rates. Some empirical evidence shows that such type of extreme events, like maybe not that notable, but like mini flash crashes, they occurred more and more frequently in recent years. So the question is, why should we care about this type of events? The short answer is, it will bias the realized volatility estimator. The realized volatility estimator is defined as the sum of squares of all the high frequency returns over a finite interval. So over a finite interval, if the number of returns goes to infinity, this is what we call the infield asymptotics. We can show that the realized volatility is a consistent estimator for the integrated variance. So this is the variance of the diffusion component in the standard Ito-Semi-Martingale model. So this is the realized volatility estimator. We know that jumps will bias the realized volatility estimator. So over the past 20 years, there are many jump robust versions of realized volatility, like the bipower variation, the truncated realized volatility having been developed. But now we find this local episode, this new type of extreme events, the drift burst type events, the flash crash, it will also bias the realized volatility. So that's the reason why we would like to propose a new estimator. So that's for the first question. For the second question, why do we like candlesticks? We like candlesticks data because firstly, because it includes more information. It includes not only the open price and the close price for each short interval, it also includes something like the highest and the lowest price reports in each short interval. So it includes more information. And also it's because of its wide availability. Compared with those high quality, high frequency data, like the top data we usually use, they're quite expensive. But for the candlesticks, 1 minute, 5 minute, 10-minute candlesticks, they are widely available on most of the trading platforms. That means that for general investors, they have nearly free access to this type of high frequency data. So that our estimator is not only an estimator which can be constructed by, let's say, academic researchers, by professional investors, it can also be constructed by general investors who have access to this type of high frequency data. So that's the motivation. That's the second question. Now, on the left-hand side, there's a screenshot of 1 minute candlesticks for one of the ETFs traded in China. So this type of data are readily available on trading platform, on some trading platform on my smartphone. So if we zoom in, if we look at a single candlestick, here we have two examples. So for each candlestick, for each small interval, the candlestick shows we have a, so first of all, there is a box. There is a box in the candlestick. We call it a real body of the candlestick. It shows the open price and the close price. So if the close price is lower than the open price, it could be a dark one or it could be a green one. If the close price is higher than the open price, we will have a white box or a red box. So this is the real body of the candlestick. So the length of the real body of the candlestick is actually the return, or more exactly speaking, the absolute return. And also for each candlestick, it has an upper wick or upper shadow, or a lower wick or lower shadow, indicating the highest price and the lowest price over this small interval. So the total length of the candlestick, the WI here, is the range over that interval, if the range of the price pass over that interval. So this is the candlestick data. Now we can think about this. If the price movement is highly directional over a short interval, how will the candlestick look like? I will show you some simplified examples. So if the price is monotonically going up, for example, if the price is monotonically going up over a short interval, we will have a candlestick like this. The candlestick will be fully occupied by the real body, by the box, because the lower price is exactly the open price, and the closing price is highest price. So there is no wick. The high is the close, and the low is the open. So this is the candlestick without wick. Similarly, if the price is monotonically going down, is monotonically decreasing, we will have a dark candlestick also without wicks. So actually, there is a specific Japanese name for this type of candlestick pattern. It means that those candlesticks are bored, without hair. So if there is a large jump accommodated by one of the intervals, how will the candlestick look like? Because the jump size is very large relative to the broadening component, relative to the volatility component. So we will observe a long candlestick with a long real body. So compared to the length of the real body, the length of wicks is very small and nearly negligible. Now we can generalize this simplified example in some more realistic case. So here I simulate some second-by-second data, log prices, and then this plot correspondingly collects all the 1 minute candlesticks. If we insert a big jump or a relatively big jump here, and we will observe a long candlestick with long real body, but the length of wicks is relatively small. Or if we insert a V-shaped flash crush type event like this, before the turning point, we will have all the dark candlesticks, and after the turning point, we have all the white candlesticks. Especially for those candlesticks near the turning point, they have something in common. They are all bald candlesticks. They have no hair. There is no wicks. So this is the place where our idea comes from. If we can construct a volatility estimator, not based on the length of the real body of candlesticks, that's the RV estimate, and also not based on the total length of the candlestick, but based on the length of wicks, this estimator should be naturally robust to jumps and this type of drift burst or flush crush type events. That is the basic idea. We would like to design a realized type estimator, not based on the returns, not based on the range, but based on the difference between return and range. So that's a wick-based estimate. Now we can define our estimator. So for each short interval with length delta n, we define the range wi and the return ri. And then we take the difference between the range and the return. There remains actually the length of Wicks, the length of upper week plus the length of lower week. So we take the difference between wi and absolute ri. We calculate their sum of squares. So we have a realized type estimator. And then we divide it by a scaling factor, which is the second moment of the range return difference for a standard Brownian motion over a unit interval, which has the theoretical value 4ln2 minus 2. We divide the sum of squares of all the candlestick weeks by the scaling factor. So this is our volatility estimator. This is the main product of this paper. We call it a range return difference volatility estimator, or a week-based estimator. So this is our estimator for the integrated variance. Now, we can show some basic theoretical results. If we consider standard continuous Ito-Semi martingale, without jumps, without drift bursts, with locally bounded drift, and with the diffusion component, the sigma and W under the normal regularity condition, we can show that our estimator under inferior asymptotics, when the length of interval goes to 0, it will be a consistent estimator for the integrated variance. So this is the consistency result. And next, we can show the asymptotic distribution of our estimator. So for the estimation bias of our estimator, it has with a convergence rate 1 over square root of delta n. The delta n is the length of the interval. It will converge in distribution to a normally distributed random variable with mean 0 and asymptotic variance at theta times this integrated quoticity. So this is a standard asymptotic distribution for a realized measure. And the theta here is, we have the theoretical value, which is approximately 0.72. Here, if you compare the asymptotic variance of our estimator with the only competitor in the literature, is the difference to return volatility estimator proposed by Anderson and co-authors in a paper published last year. The asymptotic variance of our estimator, our week-based estimator, is about 4 times smaller. But here, I didn't say we have a more efficient estimator because we use more information. But from a practical point of view, yeah, we are using some additional information which is readily available in the data set, which is very easily accessible. So, and then we can get something more accurate. We can get a more accurate estimator. So at least it's not a bad thing. So this is the asymptotic distribution of our estimate. And then now let's consider the drift burst event. So here we apply this drift burst model proposed by Christensen and co-authors in this 2022 Journal of Econometrics paper. They substitute the locally bounded drift coefficient by a locally unbounded drift term with such a form. The tau here is the so-called explosion point of bursting time. So when the time s gets closer and closer to tau, gets closer and closer to the explosion point, this term becomes very large and unbounded. If we let the C minus and the C plus, two constants, to be negative and positive respectively, we will have a V-shaped pattern in our price paths. And the alpha here controls for the rate of explosion of the drift component, which is between 1/2 and 1. And if we calculate, and with the drift burst model, if we calculate the return in the neighborhood of the bursting time of tau, it will include the contribution from both the drift component and the diffusion component. And now this term will have a higher asymptotic order because alpha should be greater than 1/2. So this term, the drift component, will dominate the return in the neighborhood of the explosion time. So this is the reason why we can observe a highly directional price movement near the explosion point. We have an example here. So this plot shows the bursting or exploding drift coefficient mu b. So with the explosion point on 1245 something. Correspondingly, we will have a V-shaped pattern in the price paths if we add this drift burst component. And for our estimator, now let's look at how our estimator behaves when there is a drift burst. So this is the estimation bias of our estimator. And this is the asymptotic order of the bias. It consists of two parts. So the first part here, the asymptotic order here, this is the order for the bias induced by the drift burst. The order is delta to the power of 1 over 2 alpha. And the second part is the order we should have under the standard setting. So if we look at the original asymptotic theory, we have the convergence rate 1 over square root of delta n when there is no drift burst, when there is no jump. So for the estimation bias, it has this convergence rate 1 over square root of delta n. It means that this is the standard order of bias when there is no extreme events, is square root of delta n. So when there is a drift burst, this term is here, is square root of delta n. But for all possible value of alpha between 1 over 2 and 1, this order is always smaller than the square root of delta n. It means that this bias induced by the drift burst is actually asymptotic and negligible and has no impact on our limit redoubt. And there is also something interesting. This bias redoubt does not depend on alpha. We can always get the standard order of bias when there is nothing, when there is no extreme event. And if we look at the similar bias redoubts for our competitor, the DV estimator, their bias redoubt not only depends on alpha, but also depends on some order of the truncation threshold. So we can achieve a better robustness from my point of view. Now let's look at some simulation redoubts. Let's look at some simulation redoubts. I simulate the efficient price using a Heston model and a compound Poisson process for the jump component. And we have some parameter choices. So for this drift burst type event, I simulate 3 types of events. So first one is a gradual jump. Compared with the discontinuous shift in the efficient price, we would like to make it a slightly sluggish. So we will have a gradual jump events like this and a flash crash event. And here I simulate something very weird, and then it's a gradual jump and with a small flash crash in the middle. And we simulate 1, 2, 3, 5 minute candlesticks for 10,000 days. We compare the final sample performance of our estimator with some competitors. And we find that our estimator tends to achieve the smallest root mean square error redoubts in 4 different cases: when there is nothing, when there is gradual jump, when there's flash crash. And for the empirical application, we integrate our estimator in the framework of a traditional Haar model forecasting. So we have 3 different forecasting targets: the traditional realized volatility, our competitor DV estimator, and our estimator itself. We put different estimators on the right-hand side of the Haar model, and then we would like to look at the out-of-sample performance. So the redoubts are quite clear. If we put our estimator on the right-hand side of the Haar model, for 3 different forecasting targets, we can expect a better out-of-sample forecasting performance because we have the smallest value for both loss functions. And if we partition the out-of-sample days based on 2 different criteria, with jumps, without jumps, with drift burst, without drift burst, and we find that when there is no extreme event, those Haar models, they perform quite equivalent to each other, their performance. But when there are jumps or when there are drift bursts, when there are some extreme events, we find that if we integrate our estimator into the Haar model, if we use our Haar model, we can always achieve smallest loss function, smallest value of loss function. So this is the empirical application. Now let me quickly summarize this paper, what we did in this paper. So in this paper, we propose a weak-based volatility estimator for the integrated variance. And then we provide some basic redoubts, consistency redoubts, asymptotic distribution. And here I use some different color to indicate something I didn't mention in this presentation. We show it's robust to both finite activity and infinite activity jumps. And we show its robustness to those extreme events, short-lived explosive trains events. We consider through 2 different models, the drift burst model, which are covered in this presentation, and also we consider something else. We also correct for the final sample bias for our estimator when we apply it in practice. And we have the Monte Carlo simulation and empirical application to show that our estimator can be applied reliably in practice. So thank you. I will probably stop my presentation here.
Thank you very much, Shifan.
Thanks.
I'll stop the recording.